Well, hello there, ladies and gentlemen. Mr. Dorfley here for our latest installment on Chapter 12, talking about forces. In the first section, we talked about Newton and his first two laws. Okay, and towards the end of the first section, and what we've done a couple days since then is have worked on calculating force by means of Newton's second law, where force is equal to mass times acceleration, and how force is going to be proportional to those two variables, mass and acceleration. To where we can have a slow-moving object but has large mass have the same amount of force as a fast moving or a fast accelerating object with smaller mass. Those two can equal out. So there's a give and take, if you will, in that regard. Now, today, what we're going to do is we're going to investigate force in a kind of a different manner. Okay. In the first section, we looked at force needs mass in order to be calculated. Okay. And oftentimes, mass and weight, there we go, get intertwined when people are talking about how much something is, whether it be how much something weighs or how much of something there is present. Okay. And, sometimes they get it wrong. Okay. There is a difference between weight and mass. And that's what we're going to talk about today. But the other thing we're going to talk about today is the force of two objects together and how an object essentially travels when it's in motion in certain scenarios. Okay, so you want to get your notes out. So if you need to get your notes out from a different room, whatever, go ahead and pause this video before I get started. And then you may start it back up once you are ready to go. You'll need a calculator today and obviously a writing utensil so you can fill in the blanks where necessary. So let's talk about weight and mass. All right. Now, mass and weight are directly proportional. There is a relationship between them. Okay. First off, mass is the measure of the amount of matter in an object. So typically, the more mass an object has, meaning the amount of stuff makes it up, the heavier something's going to weigh. But where they kind of differ is really in their underlying meaning. Weight is the gravitational force that an object experiences because of its mass. Okay, we all experience gravitational forces while here on Earth. Every object does, and other planets and celestial bodies, which their fancy name is called, they also exhibit a gravitational force. But there are some things that make it differ from one location to another, especially from one planet to another. And we're going to talk about that today as well. So, moving the location, as I stated at the very bottom here, of an object may and most likely will change its weight. Okay, you might even have some slight fluctuations here on Earth, depending on where your location is. It may not be huge in terms of its difference, but there may be. Okay, how do we calculate an object's weight? Well, it's simple. We take the object's mass, which is typically reported in grams or kilograms or anything really that has grams in it, and multiply that by free fall acceleration, otherwise known as gravity. So we get the formula of weight is equal to mass times gravity. So for here on Earth, our gravitational force, we call it little g when we are talking about, in formulas. It's really what's called the free fall acceleration near Earth. Okay, and it has a value of 9.8 meters per second squared. Very important number to know. If you don't already know it by now, you need to have that memorized because you're going to see that number probably the rest of your life. It may even come up conversation sometime. You don't know. Okay. Now, oftentimes, weight in the scientific sense, okay, is expressed in newtons. So we last saw newtons in section 1 when we're talking about force. So we can consider weight as being kind of a calculation of a specific force, okay? And so that's how we're typically going to answer our weight questions is, what is the weight in newtons? Now, there is a conversion between newtons and weights that might be off a little bit in the not too distant future. So we'll hang tight on that for now. But first, we have a couple of example problems dealing with weight on two different locations. So, as you see down here towards the bottom, we are asked to find the weight of a 58 kilogram person on the following planets. Now, much like what we saw in section 1 dealing with the mass when talking about force, and we made the very important statement that mass must be in kilograms. That has not changed. And you probably already figured that out by the time you saw us on number 3 here says weight is in newtons. Well, we know what a newton is made of kilograms times meters per second squared. So really, it's just the same formula that we saw in the first section, just with different ideas, okay? So, Earth has a gravity of 9.8 meters per second squared, and Mars has a gravitational acceleration or gravitational force of 3.7 meters per second squared. So let's first do this. I'm going to have to get out of here and get to my camera so we can do this. Okay, sorry for the quick movement there. So again, weight is equal to mass times gravity. So we saw that the mass was 58 kilograms, and that on Earth, I'll go ahead and label this Earth, okay, it was 9.8 meters per second squared. I'm going to dim this just so I'm using a new marker, a new color marker as well, so that should be okay. And so we go ahead and put this in our calculator, 58 times 9.8, and we get 0.4 right there, newtons. Okay, and it's just that. But now we are asked to find that same individual's weight on Mars. And if we go back, we see that Mars was 3.7 meters per second squared. So I'm just going to replace that 9.8. Put this as Mars. And just put 3.7 meters per second squared. Go ahead and go back to my calculator here, 3.7. And if you want to pause the video now, just to make sure that you're calculating this correctly, go ahead and pause it. But I'm going to go ahead and solve it now. That is 214.6 newtons. So we're looking at a pretty significant difference here. When we were talking about Earth, it was 568. So we're talking maybe 30%-ish, or so a little over 30% of what the gravitational force is or gravitational acceleration is on Earth. Mars, you're going to feel like you are about 30% of what your initial weight would be. Now, this isn't like saying I'm 214.6 pounds or 568.4 pounds. No, there's a conversion that you would have to do between newtons and pounds. Okay, if you're talking about 58 kilograms, and this is just a ballpark, you're looking at less than 120 pounds on Earth. Okay, so it's not crazy big. Okay, it's normal weight. All right. All right. So that's how we calculate our weight on various planets. You're going to have a lot of practice in that field. Fairly soon. But let's get back into our notes here. So you can follow along as we proceed. Oh, before we do proceed, just over here on the right-hand side, you see the various gravitational accelerations from Venus, Neptune, Earth, and Mars. Okay, Neptune, 11.0 meters per second. That's even more so than Earth. So you're going to feel even heavier, or you should feel heavier on Neptune than you would on Earth. And there's a reason why. The hint is, look at the sizes of these 4 planets. Now, size doesn't necessarily mean heavier because, there could be a larger portion of gases there. But it does give us a hint or a clue as to why we might see these differing values for acceleration of gravity. All right. So we get this next new thing. It's very fancy, but pretty easy to calculate. But it also, we don't necessarily have to use this calculation or this formula to help us get an idea of certain things here. And it's called the law of universal gravitation. And really, to put this scientifically, it states that particles attract every other particle in the universe using a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So let's stop there. Let's talk about that. Okay. Really, all this is saying is that yes, every single particle in the known universe has an attraction to any other particle. Okay. Myself and this eraser. As I place it down on my desk, according to the law of universal gravitation, there is a gravitational attraction to myself and the eraser. Okay, the eraser would be attracted to me. I would be attracted to the eraser in the scientific sense. Now, it also means that, yes, there is a level of attraction here, but now if I consider an attraction between myself and a car, okay, well, my mass is still the same, but the eraser's mass compared to the car's mass, significantly lower. So the heavier, the more mass two objects have, the stronger the attraction will be. Okay. Now, obviously, you don't see us having things just flying at us and attacking us. No. The reason why is I want you to think about it. I want you to think about why objects just aren't simply going and coming right to us and attaching themselves to us or us to other things. It's because the Earth is right here. And my attraction to the Earth is significantly larger than the attraction between myself and the eraser. So the attraction between myself and the eraser is basically wiped out, and that's why objects aren't seen flying around. Okay. But we have this other part of here says it's inversely proportional to the square of the distance between them. So what that means is the farther away objects become, the lower the attraction. And so we can have some extremely heavy objects, but if they are far away or are increasingly getting further away, then they will have less of an attractive force between them. That's also one of the reasons why space shuttles and satellites and everything like that get to remain in orbit. They've got a few things other going with them, but as they become closer to the Earth, then we start to see that attractive force take hold. Again, there are other factors that cause that to occur, but that's one of them. Okay. So if we look at this formula here where F is equal to capital G here, it's not lowercase g because lowercase g is reserved for gravity. Capital G stands for the gravitational attraction constant. Okay. And it has a value of 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. Lots of units going on there, but don't worry about them. Okay. Now, this is a constant, so it doesn't change. So once you have that number kind of down pat, that's all you need to worry about. You just look at the other numbers given to you in the problem. You have capital G times M1 times M2. This is the mass of object number 1 and the mass of object number 2, divided by the distance between those two objects squared. Okay? So, again, we don't necessarily have to use this formula to make predictions. This formula is basically used, numerically when we actually have figures in front of us. Okay, but we can still use this formula and just make predictions. So it says gravitational force increases, as one or both masses increase, and it will decrease if the distance between those two masses increases, much like I just got done saying. So No matter how small or large an object is, it exerts some sort of gravitational force on every object. We've got the Earth, Moon, Sun system is what's known as. Again, if you look down here at this image here, there's an attraction between the Earth's gravity on the Moon. There's also attraction of the Sun's gravity on the Moon. There's an attraction between Earth and the Moon, Earth and the Sun, Sun and the Earth, Sun and the Moon. So they all have an attraction to each other. But again, Moon is much smaller than Earth. And if you look at the distance, that all plays a part into this. But even though we're talking about huge objects, like the sun in particular, we still have a force of gravity that exists between the Earth and the paperclip. Again, going back to what I said, there's a gravitational force between the Earth and you. Okay? The strength of the force of gravity between two objects is determined by those two main factors, as I mentioned: the size of the two masses in question and the distance between those two masses. Okay? Now, as mass increases, again, we're still talking about gravitational force. As mass increases, the force will increase. If we have an elephant and a house cat, okay, an elephant will have a greater gravitational force than a house cat because it simply has more mass. So it's going to essentially go back to the whole idea, it's going to weigh more, okay? As distance increases, gravitational force decreases. Again, this is probably the third time so far in a matter of minutes that you've heard that statement. So these are all very important. If the distance between objects is tripled, okay, let's think about that. If the distance between the objects is tripled, then the gravitational force will actually be reduced by 1/9 of its original value. So you triple the distance between objects, now the gravitational force is only 1/9. And that is all stemming from the fact that the distance is squared. Okay? So let's look at some examples here. We have two spherical objects that have masses of 200 kilograms and 500 kilograms. Their centers are separated by a distance of 25 meters. Find the gravitational attraction between them. Okay, going back to my handy dandy little dry erase board here. Yoink. All right, sorry. Let's get this figured out here. All right. So again, we've got the formula. I'm going to darken this just a little bit. Okay. Force is equal to gravitational constant, constant G. And I like to put brackets around my other stuff other than G. Kind of keeps me in the idea of I'm going to solve the stuff in the parentheses first before I include my G in my calculation. Divided by distance squared. So our M1, our mass of our first object, was 200 kilograms. Again, it's in kilograms, so that's good. M2 was 500 kilograms, and our distance will be 25 meters. Okay. So I'm going to go back to here. So all I've done is just I listed everything, so I have to keep going back and forth between the screen and the presentation. So I've got everything listed. I'm going to start plugging everything in. So again, G was 6.67 times 10 to the negative 11th Newton meter squared times kilograms squared over let's see, did I have that right? I think I forgot to include it. Silly me, I forgot to write it down. Oh, I put the line in the wrong one. There we go. Okay. Newton meter squared per kilogram squared. All right. Back at this, folks. So just fixing my mistakes. It happens. Okay? It happens. Then we multiply our mass 1, which is 200 kilograms, multiplied by 500 kilograms divided by 25 meters squared. All right. So what I recommend you do is multiply these two first, the 200 multiplied by 500, get your, hit the equals button, divide it by what you get for 25 squared. Okay. And so this brings us over here, still calculating, 6.67 times 10 to the negative 11th, multiply by, so let's put this in our calculator, 200 times 500 equals 100,000. Okay, so you see my calculator here. And then I'm going to take that 100,000, hit the divide button, include parentheses, hit my square, I'm going to get 160. Okay, so now I'm going to take that 160 and multiply it by our G number, 6.67 times, see if you can see it, 10 to the, and make sure you hit your caret button, negative 11th. So you get a really small number. So if we count, we're going to get a force of equal to 1.1 times 10 to the negative. Again, you go over here, you go 1, 2, 3, 4, 5, 6, 7, 8. 10 to the negative 8th newtons. Double check my work. You never know. I could have made a mistake. So I'm going to actually double check my work. Okay, 25 squared is 625. Okay, so I'm just checking this here. This is the only concern here. 200 times 500 equals 100,000 divided by 625. We still got 106. Okay, always double check your work. Okay, so yeah, you're going to have some small values. Okay, so don't freak out. Don't freak out. So let's go to the presentation here. And let's see what happens. Okay, we saw what our original number was. Now it says what happens to that gravitational force if the distance is doubled to 50 meters. Okay, so I'm just going to put what I had up here, 1.1 times 10 to the negative 8th newtons. See that? That's just reminding me so we can compare. So again, 200 kilogram for our first mass, 500 kilogram for second, but this time our distance is going to be 50 meters. So going back to the formula, 6.67 times 10 to the negative 11th multiplied by, well, essentially it's 100,000 because we already know that from the last one, kilograms squared, divided by, this time it's going to be 50 squared. So bring in our handy dandy calculator, 50 squared. Again, you can, by this time you probably figure out you could probably go in your own method here. So 50 squared is 2,500. So I'm going to take my 100,000 divided by 2,500, and I get 40. Okay. So now I've got 6.67 times 10 to the negative 11th times 40. You can already guess this is going to be a much different number. And plug into your calculator, 6.67 times 10 to the caret negative 11, close parentheses, and you get force is equal to 3.0. Again, that's the number I get. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me count that again. 1, 2, 3, 4, 6, 7, 8, 9. Excuse me, 10 to the negative 9th newtons. So, just by simply doubling our distance from 25 meters to 50 meters, we get a significant reduction in the overall gravitational force between these two masses, okay? Just by simply doubling it. So yes, even though this is 1.1 and that's 3.0, this has got a smaller or less negative value of 10 than this does. So this right here is actually the stronger gravitational force. So that just goes to show you how that equation works. Okay? So again, if you need to see that again, rewind the video and rewatch it. But we are going to hop back in here and continue on our merry way. So we're going to continue to talk about free fall motion, okay? So when we say an object is in free fall, what we're really saying is, or considering, is that Earth's gravity is the only force that is acting on that object as it falls. So as you throw a ball up into the air, as that ball is falling, or even when that ball is traveling upwards, Earth's gravity is still acting on that object. And all of the gravitational force, it is directed towards the center of the Earth. That's why if we were to dig away the Earth's surface, we would continue to fall. Okay, we are directed towards the center of Earth, and then if we're on a different planet, we will be directed towards the center of that planet as well. And in the absence of air resistance, again, which never happens on Earth at least, because we have friction from air, all objects falling near Earth's surface will accelerate at the same rate, regardless of their mass. So going back to the elephant and the house cat, they're going to fall at the same rate. So what this bullet point number 4 is stating is going back to the law of gravitation, what we just worked with. Going back to the law of gravitation, this accounts for the acceleration of all objects to be in that area of 9.8 meters per second squared. So if we were to take a person with 75 kilograms as their mass, and if we've already calculated what their gravitational force is, 736 newtons, okay, my head's in the way here. If we went ahead and applied Newton's law after we calculated that 736 newtons of gravitational force, we wind up with an acceleration of 9.8 meters squared. So the law of universal gravitation gives us our value for gravitational free fall, 9.8 meters per second squared. So that's why it's an important formula. But when we have objects that are falling, we have to consider the fact that they are going to encounter air resistance. Okay. And, even though on the previous slide they just said, oh, we're going to disregard or neglect air resistance, which oftentimes when you're doing initial calculations on objects in physics, you're going to try to kind of neglect all force, the majority of the forces acting on an object, because you're trying to isolate what an object would be without any of the numerous forces acting on it. And then eventually you can start to piece in those factors, and then you start to get a better picture of an object's motion or behavior or anything like that. But when we have objects falling, we get what's called terminal velocity. And this is basically the constant velocity of a falling object when the force of air resistance is equal in magnitude yet opposite in direction to the force of gravity. So basically, as that object is falling, the air resistance is working in the opposite direction. Okay? And eventually, if given enough time, the air resistance, the closer you get to Earth, will start to increase to the point where the opposing forces are going to cancel out, and you will no longer continue to increase your velocity. You'll come to a normal, steadfast value for velocity. Okay? When terminal velocity is reached, a falling object is also not accelerating anymore. It's not saying that it's not moving. It's just we're not seeing an increase in speed or velocity or acceleration of that object. And this usually is only obtained when we have a high enough distance off the Earth's surface when an object falls. Skydivers tend to dive out of planes at a pretty high altitude to the point where they could reach terminal velocity. But if you're too close to the ground, you won't achieve terminal velocity. We'll watch that video at some other point. Okay, let's look at terminal velocity and some other free fall examples. So let's look at astronauts in orbit. This is always a fascinating topic. Okay, now oftentimes we say that astronauts are weightless and they're floating out there in space. But that's not the case. They still have weight, okay? Obviously, because they still have mass. And we said mass determines weight. But what's happening is they're really just in constant free fall. The vehicle that they're traveling in, it's not a shuttle anymore. They discontinued that about 6-7 years ago, roughly, maybe even 8 years at this point. But that apparent weightlessness that the astronauts feel is because whatever vehicle they are in is constantly falling towards Earth with the same acceleration that they have. So they're constantly going like this. If you've ever been in an airplane and it suddenly has some turbulence or whatever and it drops, you get that kind of like, oh, you feel like you're almost floating. Well, that's what's happening. You get the same experience on a roller coaster when a roller coaster goes up over a hill at really high speeds. Your body feels like it's weightless because you're no longer really attached, but really you're just falling. Basically, what keeps the shuttle or what kept the shuttle or any other body that's out there in orbit around Earth in orbit is it's going so fast that it is just constantly going around the Earth like this. The Earth's trying to pull it in, but it has so much momentum and inertia that it's going to stay at its current speed. But it's still always falling. Okay, it has something to do with also the curvature of the Earth as well. So they are constantly falling. That's why they have this apparent weightlessness. Going back to the skydiver falling to Earth without a parachute open, skydiver accelerates towards Earth due to gravity. As the skydiver accelerates towards Earth, their velocity increases and they experience a force pushing against them. Okay, so if you've ever had your hand out of a car window, when you're going slow, the wind isn't so crazy, but as soon as you start picking up speed, you are having a greater amount of air resistance impact your hand, and sometimes it's louder and it's harder to hold your hand out there. So terminal velocity, if we put numbers to it, it's about 320 kilometers per hour, or 150, 140-ish miles per hour around there. Okay. So it's pretty fast, but it's not the fastest thing that we have around here. And then the reason why we slow down is because we eventually, hopefully, fingers crossed, our parachute opens, and it's going to increase the air resistance experienced by the skydiver because it's covering a much more open area, and so it has more surface area for that air resistance to affect. And then one of the last things we're going to talk about is projectile motion. Again, this is kind of where the idea where space shuttles or satellites or the International Space Station are allowed to stay in orbit as well. Projectile motion is the curved path that an object follows when thrown, launched, or otherwise projected near the surface of the Earth. If you throw a baseball, shoot an arrow, throw anything, launch a cannonball. How about that? Launch a cannonball near the surface of the Earth. You're going to notice that it doesn't just keep on going. In fact, its gravity is having an impact on it. So is air resistance, but gravity is what really gives it the curved path. Okay, there are two components of an object that is considered to have projectile motion. It has a horizontal component as well as a vertical component. If we look at this image of the pitcher down here, number one here, after the ball leaves the pitcher's hand, its horizontal velocity is constant. And we say that because after you throw it, that ball is not getting any additional force provided to it. Okay? There's nothing else that's going to be pushing it. It's all coming from what you did initially. Next, the ball's vertical velocity increases because gravity causes the ball to accelerate downward. And when you have these two components, the horizontal and vertical, you get this overall motion that makes a curved path, or a projectile motion is a curved path. Okay? Now, horizontal motion is the motion that's perpendicular at 90 degrees angle to the Earth's surface. Okay? Or I should say the Earth's gravitational force. So they're kind of going like this with each other. Vertical motion is one that's oriented towards the center of Earth. It's the up and down motion of an object. Again, it's force of gravity is what's pulling the object downward. of 9.8 meters per second squared. So, while throwing a baseball, we see a projectile motion when the ball is thrown straight out of the player's hand. That's the vertical motion of it. The horizontal. The vertical motion is caused by Earth's gravity, causing the ball to accelerate downward. They create that curved path like we saw. Going back to the orbiting object, the forward movement of the shuttle is, I'm going to move my face here. The forward movement of the shuttle is going to allow a constant speed. So it's going to continue wanting to go forward. The vertical motion is going to be experienced by free fall motion of gravity, pulling the orbiting object downwards. But because of these two combined forces or motions, the forward or the horizontal and the vertical, we end up getting a curved path. That curved path allows for the orbiting object to continue to go around the sun. Now, if that orbiting object slows down to a certain speed or velocity, then it will not be able to overcome the vertical component, and that's when we're going to see the orbiting object start to re-enter Earth's atmosphere. Okay, lots of stuff. Again, if there's anything that you missed in your notes, go back, rewind, pause if you have to, have a calculator out ready. Again, make sure you are staying on top of your notes. Everything that is either on a quiz or a test, I've said it before, comes directly from our notes or things that we have done in class. So, as I attempt to close out of this, we are going to go ahead and wrap up our discussion on this. So again, stay on top of your notes, keep paying attention to any new posts, and I will see all of you, or at least most of you, later on. Have a good one.